Well, if we can test for the value of the regression parameters, we can also build confidence interval for these regression parameters. We can also build something called prediction intervals. We haven't talked about prediction intervals yet. The steps are the same as those we saw in Chapter 5. You start by finding a point estimate, let's call it W here, for a given parameter, beta, or the prediction Y for the prediction intervals. You will find an appropriate standard error for this parameter based on the point estimate. You select a confidence level alpha. You find the appropriate critical value K alpha divided by 2, if you're interested in two-sided intervals, which is all we've really talked about. You find the appropriate critical value K alpha divided by 2. We're only going to be talking about two-sided intervals here, not half-open intervals. And the K represents the fact that depending on the standard error, you might be using different distributions to compute the critical value. And once this has been done, you can compute the 100 times 1 minus alpha percent interval of interest, either confidence or prediction, as being the point estimate W plus or minus the critical value that you found times the standard error of the point estimate for the parameter of interest. Let's start with the confidence intervals for the intercept and the slope. These are the easiest ones to compute. We've estimated the error variance with the mean squared error, sigma hat squared. That requires us to use students' t-distribution with n minus 2 degrees of freedom, right? The degrees of freedom here, basically the denominator of the sigma estimate. And so we use the data to estimate two parameters along the way in order to get the sigma hat squared. The confidence intervals for beta 0, beta 1 at a confidence level of alpha are simply the point estimate B0 and B1. These are the things we've evaluated. These are the quantities that we've evaluated as our best guess given the data that we have for the true slope and the true intercept, plus or minus the critical value of the student t-distribution with n minus 2 degrees of freedom at alpha divided by 2 confidence levels. And we multiply that by the appropriate standard error of B0, the standard error of B1, and we have formulas for those. So that gives us confidence intervals for the true value of the intercept and the slope. And of course, the original remarks about what it means to be a confidence interval still applies. If this is a 95% confidence interval, I'm not saying that I'm 95% sure the true value is in there. What I'm saying is that if you follow the same procedure when you compute the confidence interval from different samples, 95% of the time, the true value of the parameters would be found within the confidence interval that has been built. But you get a different confidence interval for each sample that you use. If we use the fuels data set again, build 95% and 99% confidence intervals, both for the slope and for the intercept. So we need B0, B1, the standard error for B0, the standard error for B1, the critical value of the student t-distribution with 18 degrees of freedom, 2 fewer than the number of observations, which was 20 at the confidence level alpha divided by 2, which would be either 2.5% or 0.5%, depending on whether we're working with the 95% confidence intervals and the 99% confidence intervals. All of these values can be estimated from either the data or by looking up the critical values in tables for the student t-distribution, or by using R and the QT function to come up with the critical value. And then it's just a matter of substituting these values into the formula. There's barely any thinking required. At the 5% confidence level, we have for the intercept the intervals 70.93 and 77.63, and with our estimates 74.283 being the midpoint of that confidence interval. And for the slope, we have 12.18 to 17.71. Again, 14.947, the estimate for the slope being the midpoint of the interval. It's the estimate plus or minus 2.10, which happens to be the critical value, 95% confidence interval of the student t-distribution with 18 degrees of freedom. And then for each of those, you use a different standard error, the one for B0 and the one for B1. You repeat the same procedure for the 99% confidence interval, you will get wider confidence intervals. All else being the same, the sample size being the same, the standard errors being the same, and they are because you're estimating them with the same data and the same estimate for the variance, you will get wider confidence intervals if you are looking at a higher 100 times 1 minus alpha % value. For the slope, the interval is 11.15 to 18.74. Now, we don't know what the true value of beta 0 and beta 1 actually are, so we can't verify here if they are indeed within the confidence intervals or not. It could be that we were unlucky with our choice of observations. Perhaps we got some observations that weren't as representative as they could have been. We don't know. We can also build a confidence interval for the mean response. Perhaps here we're interested in estimating the expectation of the response given a predictor. In practice, there might be more than one response at a predictor, right? If you replicate an experiment, you will run through a succession of duplicate predictors and, well, you might actually get a different response every time you rerun the experiment. Might not be a huge difference in the response, but if there's a stochastic element to it, a random element to what you're doing, you would expect that there could be different responses. And so you might want to predict what the average response would be at a given point. The predicted value, not the expectation, the predicted value, you can read it directly from the regression line. The regression line tells you what to expect at a given predictor level, right? I have a bunch of x's here and I picked this one here, x0. My estimated y0 is the height of the line of best fit at that specific level, x0. That's the whole point of linear regression. But in practice, you might have a number of actual values. For a given predictor value x0, the distance between the estimated value, the line of best fit we built using the data that we have at points other than x0, and the true regression line, the line that is built using the beta 0 and the beta 1, which we do not have, well, you can compute it as follows. It's the difference between the estimate and the true value. That would itself be a linear function, b0 minus beta 0 plus b1 minus beta 1 times x0. The trick, of course, is that we do not know beta 0 and beta 1 here. This is the true values. But we can compute the expectation of that prediction. It is just going to be what the true value would be. And we can also compute its variance. It looks a little bit like the variance we built. We talked about the variance of b0, sigma squared times 1 over n, plus the square of the difference between the level of interest and the average value of x divided by sxx. This is actually fairly difficult to demonstrate. We're not going to show that this is the case. One of the things I will mention, though, is that the variance of this expression would not be the same as the sum of the variance of b0 plus the variance of b1 x0. If b0 and b1 were independent of one another, you could write that the variance of this sum is equal to the sum of the variances. And this would be interesting because this expression here is exactly this expression here, and it would be easy to compute the variance of this predicted value. But they are not independent of one another. B0 directly goes into the computation for B1. Or another way to look at this, B0 and B1 both use the values of xi and yi in their computation. So they cannot be independent of one another. They are dependent. And so you can't just use this sum here to compute the variance of the predicted response. Which is why you get this funky expression. Well, if you want to build a confidence interval for the mean response, we use the usual critical value of the student t-distribution with n minus 2 degrees of freedom. at a confidence level alpha divided by 2. And then we get the following expression. It is going to be the estimated response, B0 plus B1 x0, plus or minus the critical value times the square root of the variance of our expression. And it's t rather than z because we are estimating the true variance here with the mean squared error, SSE divided by n minus 2. Looks like a complicated formula, but again, you know all of these terms. You can look this one up in a table or using R. This is just B0 plus B1 x0, and you know B0 and B1 and x0 is given in the problem. Sigma hat squared, you have computed it before. SSE divided by n minus 2. 1 over n, you know how to compute this. You have the n value. X0 is given. X bar, you can compute it. S, XX, you can compute it. All of these things are easy to compute, put together. You just need to be careful not to make computational error along the way. So for the fuels data set, the 95% confidence interval for the mean response is going to be this expression here. And you'll notice this is an expression that has a variable. If I've given you a specific x naught value, say this one here, you can go up here, get your response, so that's this part right here, and then compute the width of the confidence interval. It's this part right here. But if you were to pick a different x0, you would have presumably a different width. As a function of x0, this actually gives you curves that are not straight lines. This part here is a straight line, the center is a straight line, but if you look at the actual outline, this expression here is not going to be a straight line. It's the square root of quadratic. And the square root of quadratic is not a straight line per se. So as you get further and further away from the mean value of x, this quantity here is going to become larger and larger. And so you would expect that as you move away from the mean value here, the confidence intervals will get larger. If you think about it, that is not unexpected. Near the mean value of your observations, you think you have more measurements. In general, the mean value is the central tendency of your measurements. Central tendency means you expect to have more measurements around it. If you have more measurements around that specific point, you have less uncertainty. And if you have fewer measurements away from the mean, which you would typically expect, then you have more uncertainty because you don't have as many measurements to cap the confidence interval. Now, what if you wanted to predict new observations? Not the mean response, but the actual response. Your best bet is going to be the mean, the line of best fit, right? So your prediction at a point x0 would be y hat, b0 plus b1. Now, if y without the hat is the true future observation, the true new observation at a point, and y hat is the predicted value given by the line of best fit, then the prediction error would be the difference between the true value and the predicted value. And if you work that out, you will get beta 0 minus b0 plus beta 1 minus b1 x0 plus epsilon. And this has a normal distribution with zero mean. Right? On average, you would expect the true value to be as likely to be above the line of best fit as it is to be below the line of best fit. And it has a variance which is given by sigma squared 1 plus 1 over n plus x0 minus x bar divided by sxx. You'll notice a difference here, and this isn't quite the same as the variance we had in the previous case. This one here, there's an extra term, 1, which is given because we are not computing quite the same thing. When we're computing the confidence interval for the mean response, we are subtracting the true expected mean from the computed expected mean. There is no error term here. When we compute where the new observation should be, we are looking at the difference between the true expected value, which would be the true line of best fit, minus where it actually ends up falling, and there's an extra term in here, a noise term. And this noise term has a variance component. It's sigma squared. This is where the extra sigma squared component comes in. That has the effect of giving us a larger variance for the prediction error than we would get otherwise. And so you have exactly the same formula as before, the same expected value, the same critical value, the estimate here given by the MSE, but the variance has changed. We have an extra term of 1, and that actually increases the quantities. Like 1 over n tends to be fairly small. This thing tends to be fairly small. Adding 1 to it actually makes a pretty big difference. So for the fuels data set, the prediction interval, so the 95% prediction interval, would be obtained by replacing all of the quantities in here by their appropriate values. We do have the MSE at 1.18, we have B0 at 74.28, B1 at 14.95. The critical value for 95% doesn't change, it's still 2.10, N is 20, X bar is 1.12, SXX is 0.68. None of this has changed, but now we add an extra term 1 here. And if you look at what the prediction interval will look like, we're getting a substantially larger interval. I've left the confidence interval for the mean response in gray. The prediction interval says, yes, the mean would be likely to be found in the gray region, but there might be some values that are quite far from the gray region, which is what you would expect. In general, for a given confidence level, the prediction interval is wider than the confidence interval. And that shouldn't be a surprise, right? Because the central limit theorem has shown us that the mean response has a smaller variance than the predicted response.